talk is by Benjamin Quiring from the University of Maryland. And he's going to tell us about webs and flow-directed well-typedness.
Should this be mirroring right now? Great. Cool. Yeah, so this is Webs and Flow-Directed Well-Typedness Preserving Program Transformations, a nice long title. I'm Benjamin, and this is joint work with my advisor, David Van Horn, and my other mentors, Olin Shivers and John Reppy. So let me first tell you about flow-directed program transforms, because that's what this talk is about. So I'm going to use a case study of dead parameter elimination, which is a transformation you might want to do in your compiler that eliminates parameters that aren't used. When you do that, you have to eliminate the corresponding argument. So if we define a simple function f that has a dead parameter y, if we know where f is called, then we know that we can delete y and the corresponding argument that we pass to that. Yay. But if we move to a higher order setting where we like to write code, things get a little bit more complicated. So instead of having one function, we have two functions, and now they functions that it's constrained with because it shares call sites. And it also involves you knowing where those call sites are. And we just saw a talk on this nice partition of the analysis versus the compiler sort of interacting. So a flow analysis is the thing that goes and finds the information and gives that back to the compiler, and then the compiler is going to go do optimizations based on that. So this idea of constraints is one of the central ideas of the paper, and is something that we call webs. So for any program that you might want to compile, you can construct a bipartite graph between the functions and the calls, where an edge exists if it's possible that a runtime call can be, or that call could call that function at runtime. So the webs of the program and the webs of this graph are the connected components of the graph, and I'll color them here. And webs are important because they're the unit of transformation, which means that if you transform one element of the web, either a function or a call, you have to transform all elements. For example, if we transform function 1, then you have to transform call 1, which means you also have to transform function 2 and call 2. So assuming that we have some analysis that can find this information for us, find these connected components, we can annotate our internal representation with them so that we can go and write compiler transforms that consume this information. So it's very simple to do that. I'm going to give myself a set of what I call web identifiers, which is this meta variable u, which refer to concrete webs like 1 and 2. And on every function and every call, I'm going to annotate those with a web. And you can think of these webs as being representatives of sets of functions and calls. And these annotations are subject to the constraint that at runtime, if you're at a u annotated call, it has to be invoking a u annotated function. And that's the crucial piece. I call these the web constraints. That's the crucial piece of soundness information you need. So if we revisit the higher order program example, but we annotate it with webs, we can do this transformation again. So this time, since we have the web information available, we know that if we modify one function in the web, we have to modify all of them. So the first thing we're going to do is inspect all functions in the web to make sure that they both have the dead parameter, and indeed they do. And then we can follow that up with a secondary pass over the term to actually delete the dead parameters and the dead argument. And that works great, and we can use our annotations to guide that. So if we were to write a piece of code to do that, it would first consist of a transformation that traverses over the entire term and checks to make sure things are dead. And then we'd follow that up by a secondary pass excuse me, a secondary pass that modifies all functions and all calls inside of that web. And in general, if you do these flow-directed or web-based program transformations, you're going to have a first check that's going to traverse the program to check some condition or compute some information about each web. And then you're always going to follow that up by a traversal to actually do the rewrite, 2 separate phases. So the next question is, how do you actually find these webs? And a classic approach is to use something like my advisor's abstracting machines framework, which is based on abstract interpretation. But if you care about efficiency, this can be really difficult to maintain and indeed to even make efficient. And if you have complicated semantics, that could also complicate your life with designing the analysis. And when it comes to typed languages and doing the actual transformation, you have a couple other challenges. For example, you don't just have to modify the term, you also have to modify the types. And since terms flow through types, you have to track how that's going on and modify the types accordingly. So if in this x parameter, we modified some function that flowed through this type, then we'd have to figure out how to transform that accordingly and track that during the analysis. And that can be done, but it's just extra work. That's kind of annoying. The second issue, and this is more critical, is that the flow analysis is often more clever than the type system, than the underlying type system. So I have an example here to demonstrate it. I define a choose function, which returns one of 2 elements depending on a Boolean. And in the program, we always invoke this with true, which means in particular that H is always going to refer to F. It's always going to get the first thing from choose. And so our web just consists of this one call and this one function, which means it's perfectly fine to delete this dead parameter. But if we do that, then we're left with F and G, which have 2 different arities, and choose still says that it could return either of them, even though that's technically not possible at runtime. But the underlying type analysis is having an issue with that because they have different arities, and there's no way to reconcile that. Well, unless you did some extra clever things with G. So I'm going to present a very simple type-based approach that's going to be really easy to implement and quite efficient, and we're going to see that it's quite efficient, or it's quite effective in practice as well. So it's super simple to do. You're going to take your annotated language, and in addition to annotating functions and calls, we're also going to annotate types. And when we modify the typing judgments, we're just going to make sure that the annotations line up between the functions and the arrow types, and between the calls and the arrow types. So we can see these, you have to have the same annotation. So the annotations on the arrow types are essentially carriers of proof that the function annotated with a certain web is going to match the annotation at the call site where it's eventually invoked. And that's the entire analysis. It's that simple. So for inference, it's also super easy. You're going to take your term and annotate it with fresh identifiers everywhere. And then you're going to type check the program and collect which of those identifiers have to be the same. And then you're going to merge them all together with something like a union find, and then